All right, so yesterday we finished up talking about the Gabriel synthesis. And the Gabriel synthesis, if you remember going back here, was a response to the use of sodium azide. We said that you could make primary amines by doing SN2 substitution with sodium azide, and then reduce it using palladium on carbon and hydrogen, or LAH. But the big problem here was that this is very, very toxic, and it evolves a lot of gas. Both of those aren't suitable for large-scale reactions. The Gabriel synthesis is a lot better in terms of toxicity. It avoids the generation of gas, meaning you don't have to worry about pressure buildup. But what's one potential downside to the Gabriel synthesis? Think about something I normally ask you to calculate for your lab reports. Atom economy. Look at the atom economy here. It's pretty crummy. So it's not the best reaction in terms of atom economy, but sometimes it's a little bit of give and take. As a chemist, you have to choose something that won't kill you, but you want to try to make it as green as possible. All right, so let's look at the mechanism for this. And the mechanism is very straightforward. So we need to start out with phthalimide. And then what we're going to do is first treat this with a base. Typically it's sodium hydroxide or potassium hydroxide. And like I said yesterday, we're going to pluck off this proton. And the reason we're grabbing that proton is it is resonance stabilized across both carbonyls. So now we've got a nitrogen with a negative charge. That nitrogen, even though it's resonance stabilized, is still a very good nucleophile. So in the next step, we're going to do our SN2 chemistry. This nitrogen is going to attack the backside of that alkyl halide. You have to be careful that the alkyl halide isn't too hindered. So now we've formed a new carbon-nitrogen bond. And if you remember, we had two different reaction pathways for quenching this. One was with acid. And with acid, I'm just going to skip this, but if you remember going back to chapter 21, we saw that we could hydrolyze amides using acidic conditions and heat. So I'm just going to write acid and heat. When you do that, you're going to hydrolyze that amide on both positions. You're going to get a diacid out. Along with your new primary amine. So that's option one. Option two, instead of using acid and heat, which is sometimes very slow, you can use hydrazine. And I'm going to just kind of gloss over this mechanism too, but hydrazine is a very good nucleophile, and it can actually transfer off the nitrogen. And you may see both of these in your textbook or on sapling, so I did want you to be familiar with both mechanisms. But in either case, the main goal is to get your primary amine. Make sense? All right, so now I'll give you a little bit of a warm-up synthesis problem to think about. And our goal is to make a primary amine starting from an alkane. And so I'll give you a starting material. The starting material I want you to start with is this alkane. What would this be called? Yep, 2,3-dimethylbutane. So the longest parent backbone is 4 carbons. We've got a methyl group coming off of carbon 2 and 3, so it'd be 2,3-dimethylbutane. And now our goal is to make a primary amine, and let's try to name this primary amine too. So I'll give you a minute to think about the synthesis and the naming for each of these. Let's do the name first. So what would the name of our desired product be? So 2,3-dimethyl, that hasn't changed. And then what? 1-butanamide. Or butanamine, sorry. There we go. You do have to indicate the amine position by indicating that it's coming off of carbon 1. All right, so we're going from 2,3-dimethylbutane to 2,3-dimethyl 1-butanamine. I keep on wanting to say amide. All right, so I'll give you a little bit of time to think about this, but try to propose a synthetic route. All right, let's try to do this as a class, and let's just work backwards step by step. So we just saw a route through which we can make primary amines using the Gabriel synthesis. So for example, to make this amine, we would first start out with phthalimide. Let me clean this up a bit. And we need the base as step 1. So I'll just say sodium hydroxide. And then for step 2, we need an alkyl halide, and we can tell based on the alkyl halide that the halogen used to be where the amine was. So it's going to look a lot like our final product, but I'm just going to put a halogen there. And then what should we use for step 3? I'd just use hydrazine just because it's fast. And if you do this, you can end up with your final product, which is right here, whoops, and H2. But now we need to figure out how to make this alkyl halide. So let's do that down below. We now need to figure out how to make this alkyl halide. And I'm going to put the alkyl halide intermediate that we need over here. What would the precursor be that could be used to make this? Or can we just halogenate our starting material to make this? Why can't we just halogenate our starting material? So for example, why can't I just do Br2 and UV light? It would go on one of the tertiary carbons, that's right. So what we need to do is we need to have a different intermediate. What intermediate do you think would be most appropriate? Probably an alkene. Okay, so let's pick an alkene. So for example, we could choose this alkene, and what reagents would we need? We need HBr, but we want it to go anti-Markovnikov. We'd use a peroxide, so ROOR. Now we need to figure out how to get from our starting material to this alkene. Can I just treat this with a strong base? No. Nope, we don't have a leaving group installed, so we need to install a leaving group first. So maybe we do purposely halogenate that tertiary carbon. So if we halogenate it, right, we would halogenate one of those tertiary carbons that I've highlighted in green. And then how do we get the alkene off of that specific location? Do we want a big bulky base or a small unhindered base, or does it matter? Bulky base. Okay, so we did halogenation, followed by elimination, followed by anti-Markovnikov halogenation, followed by a Gabriel synthesis. It's kind of a mouthful here, but it's a lot of good review chemistry. Does that make sense? Yep. Yeah, you could do the azide substitution rather than the Gabriel synthesis. Like I said, it depends on the scale you're doing it. Sometimes you do see the azide reaction done still. Yep. All right. So one big limitation to all of this that I've shown you, though, is if you look up at each of these reactions, we were always making primary amines. So then the question is, well, what if we need something beyond a primary amine? We can't just alkylate it very easily, or else we over-alkylate it on accident. And so in order to work around this, we have to do a new reaction called reductive amination. Yep, it is fun. And let's take a look at the overall idea of reductive amination. And the idea with this is you want to start with a ketone or an aldehyde, either one. What we're going to do is we're going to treat this with some sort of buffered condition along with an amine. In this case, I'm just going to pick the simplest amine. We're going to do ammonia. And we're going to drive off water during this reaction. What sort of product do you think we'll make? Not an amine. Not an enamine. We don't have a secondary amine. An imine. And if you don't quench this, you can actually leave it as its charged species, right? And this is referred to as an iminium ion. Because this is under relatively acidic conditions, it's fine being protonated, all right? And then in the next step, the whole goal is to do a reduction. When you do a reduction, you can convert that double bond between the carbon and nitrogen to a single bond. And you can end up making an amine this way. The nice thing with this is you can use primary amines or secondary amines, and so you can work your way around outside of primary amines. The interesting thing with this is we have to be super careful with the reductants that we use. But let's take a look at some problems. Hydride reduction with NaBH4 or LAH would be problematic. And I'll show you why. The reality is, during this iminium ion formation, you're typically doing it in one pot with your reducing agent. So let's take a look at what I mean by that. So let's say I try to do this with my buffered acid, my ammonia, and let's say I use NaBH4. What do you think the problem is going to be? It's going to reduce the carbonyl before it has a chance to even form the iminium ion. So your carbonyl will get reduced first. So this is a pretty big problem. Ideally, you want to do this in one pot. You don't want to reduce the carbonyl. You want to get your iminium ion and then reduce that. So in order to accomplish this, what you really need to do is you need to use a gentle reducing agent, something that's more gentle than sodium borohydride. So let's take a look at some new reducing agents. And I'm going to put the strongest up here. What's the strongest reducing agent we've seen? LAH. So LAH would definitely be the strongest, followed by NaBH4. That was a little bit weaker. That works for aldehydes and ketones, but not esters and carboxylic acids. And then down here, we're going to put weakest. And the new one that we haven't seen, but is weaker, is NaBH3CN. This is sodium cyanoborohydride. So let's take a look at why this is a little bit weaker than NaBH4. So if we think about this, right, we need a hydride donor, something that's willing to give up electron density. In this case, what's going to slow it down and not make it as willing to give up electron density? Yeah, that's really the only difference, so it has to be this. So if we think about this, this electron withdrawing group makes the reduction slower and less aggressive. So much so that sodium cyanoborohydride really isn't that good at reducing aldehydes and ketones. It's just not aggressive enough to reduce an aldehyde or a ketone. However, it will reduce the iminium ion quite well. So let's take a look at this. So now, if we take that same ketone that we started with before, you can run this all in one pot. Use NaBH3CN, that's the sodium cyanoborohydride, and you can use this to get your primary amine. Does that make sense? So that's the whole idea behind reductive amination, is forming an imine or an enamine and reducing it very quickly. So let's take a look at the versatility of this. So this reaction is versatile. And I'm just going to use a generic ketone with two R groups coming off of it. But we just saw that this can be used under buffered conditions with ammonia and sodium cyanoborohydride to make a primary amine. Or you can do this with a different primary amine and sodium cyanoborohydride. Now we've got a secondary amine. The secondary amine still goes through that iminium ion intermediate, and then that iminium ion gets reduced. And then last but not least, if you react this with a secondary amine and acid under buffered conditions, along with sodium cyanoborohydride, you can now make a tertiary amine, but this time, instead of going through a true imine, you're usually going through some sort of enamine or iminium ion, where you do have carbons coming off that upper nitrogen. So this can be used to make a tertiary amine. It does depend on the conditions. Quite often you stop at the iminium ion and then reduce it immediately when it's at the iminium ion, though. Does that make sense? All right, so let's take a look at this in application, and I've got a few cool examples. So I'll do examples in pharmacy. And the first example involves this intermediate. Bear with me while I draw it. Has a stereocenter down here that's a wedge, another aromatic ring down here, chlorines that are ortho to one another. And with this, you can treat it with methylamine. And when you do this, you're going to convert that carbonyl group off of the very top into a secondary amine, right? So let's determine what that product looks like. Oops. And if you notice, we've created a new stereocenter up here. This drug, when they make it, they actually leave it as a racemic mixture. This drug is called Zoloft. sure many of you have heard of these before. There's a huge class of antidepressants and stimulants out here that have really similar structures, usually with an amine fairly close to some sort of aromatic group. So phenethylamines or amines like this tend to be psychoactive. Zoloft is racemic though. All right. The other example that's a prime example of what not to use chemistry for, but it's in the Klein textbook, so you can't report me, is this one. How many people have seen Breaking Bad here? A few people? Every year it gets lower and lower. It's kind of sad. It was one of my favorite shows. But in Breaking Bad, they go out and they steal something called P2P. Why do you think they called this P2P? Let's name it. What would this be called using IUPAC naming? So we want to number our longest carbon chain. 2, 3. We've got this group coming off of carbon 1. Okay, so this would be phenyl. 2 propanone. So in the show they call it P2P. And so they steal this as a pharmaceutical reagent. The reality is this is so strictly controlled that if you tried to purchase any of it, you'd have the DEA on your doorstep within an hour. And if you're a fan of the show, you probably remember the scene where they rob a train car. And in that scene, they're stealing methylamine. However, in the show, they don't do reductive amination using sodium cyanoborohydride. They do a completely alternate route. And when they did this, they were able to convert the ketone to an amine. That looked like this. Sorry, let me draw this out nicer. And this is what they ended up making in the show. And if you're familiar with Breaking Bad, this is methamphetamine or just amphetamine. And it, like I said previously, if you look at this, anytime you've got an aromatic ring with an ethyl group off of it with a nitrogen attached to that ethyl group, it tends to be psychoactive. If you take, let's say, ADD or ADHD drugs, most of those drugs are phenethylamines as well. The dosage obviously impacts the strength of these drugs, but things like Adderall are phenethylamines, Ritalin is a phenethylamine. They all have this similar structure, and so it's widely used in the pharmaceutical industry. Does that make sense? All right, so I'm not encouraging you to try this at home. In fact, it'd be very difficult to try it at home, and it'd be incredibly dangerous too. All right, so let's do some retrosynthesis. Does anybody know when the first amphetamines were developed, actually? Or this is a completely side story. I read about it. It's crazy. The Germans gave it to soldiers in World War II. They'd get them nice and high before sending them into battle. It turned out not to be the best idea, believe it or not. They actually gave it to U.S. pilots, too, to keep them awake during long missions. They were called go pills, but then they realized that pilots were quickly getting addicted to them and thought that wasn't the best idea. All right, so let's propose a synthesis of this amine. This one looks a little bit more complicated. So I'll give you a minute to think about how to make this amine using reductive amination. Really, it's the only way we can make it, given the chemistry we know. Let's try this as a class, and hopefully that'll get us on the right page. And I'll show you some tricks whenever you're doing retrosynthesis with amines. It's really simple. You could say, all right, let's sever that bond, for example. And if I sever that bond, so I'll actually color code this. That means that that bond used to be a CO double bond, right? So for example, you could have something that looks like this. going to try to spread this out. Oops. Like that, right? And that could actually react with itself, form two ring systems, and we could do reductive amination. So that could work. Let's try another one. We could sever that bond on the left of nitrogen. If we did that, then that bond over here used to have been an aldehyde. And then this ring system over here must have had an amine on it like that. Does that make sense? And then the last one would be this one in blue. So same idea. And it would look like this, right? The other thing you might notice is that these two are identical. Okay, so looking at these possible intermediates, which do you think would be the easiest working backwards with? The bottom one or the top one in red? I'd probably say the bottom one. It'd probably be easier. All right, so let's plan this out. And so, for example, we could say, all right, we need a ring that contains an amine on it. And then we need 1, 2, 3 carbons, and then we need an aldehyde coming off of it like this. And do we need any sort of external amine for this reductive amination? No, the amine's actually tied onto its tail, so we don't want that amine on there. So all we really need is some sort of buffered low pH condition along with sodium cyanoborohydride. And you can use this to make this relatively simple ring system where you have a nitrogen in it. So really these retrosynthesis problems for reductive amination look much harder than they actually are. Try to retrosynthetically plan in a similar way we did, where you cleave various bonds attached to that nitrogen and turn them into a CO double bond. It'll make your life a lot easier. All right, want to try a harder synthesis problem?
Oh, yeah.
Oh, yeah. I like the enthusiasm. All right, this time we're going to start out with methyl cyclohexane. And our goal is to get to a more complicated amine. And there we go. So I'll give you some time to work on this, but this one's a bit more complicated. All right, since we are running low on time, let's work backwards on this really quick. And like I said before, you can identify bonds that are attached to the nitrogen, like this one, and say that used to maybe be a CO double bond. Same thing with this one over here. So let's work backwards. Say, all right, that means that we must have still had this parent backbone, but off of each of these positions, we maybe had some sort of CO double bond like this. So maybe there is an aldehyde on one side and a ketone on the other. Make sense? Still the same number of carbons, but now this red carbon right here has a CO double bond, and this red carbon over here has a CO double bond. All right, now we need to identify the reagents. What sort of reagent do we need? We know we need acid, and we know we need sodium cyanoborohydride. What amine do we need? Have to be dimethylamine, right? So HNME2 or HNCH3, either way. All right, so now we've got this intermediate. Now the question is, how do we get from our starting material to an open chain form? Ozonolysis. So we saw that a few times, so let's figure out the ozonolysis route that we must have needed. So maybe O3 as step 1, followed by DMS for step 2, that's dimethyl sulfide. And if we did that, we must have had some sort of alkene. And if you remember going all the way back to second term, you can cut that double bond. and result in an aldehyde and a ketone. Okay, so that works. Now the question is, how do we get from our alkane to that alkene? We can't just treat it with strong base.
Install a leaving group into.
Yep, so we need to install a leaving group first. The only way we can do this is to install it on the most substituted carbon, so that would be with radical halogenation, BR2 and UV light. And now we need to figure out what conditions we need to do the elimination in order to get the double bond on that location. So what base?
NaH.
Yeah, we need a small base. We don't want terbutoxide because then we get our Hofmann elimination product. So something like NaH might work well here. All right, so this looks like a pretty good synthetic route. Now we're capable of producing a lot of different amines using one simple reaction scheme. So tomorrow when we come back, we're going to talk a little bit more about amine chemistry, and then we'll get into Hofmann eliminations.